let's bring this all together and talk through how to compare multiple molecules' intermolecular forces. And we're doing this because we want to have an idea of which molecules would have stronger or weaker intermolecular forces comparatively, because we'll then take that information and apply it to phase changes and other physical properties to compare and say, well, I think this molecule will have a higher boiling point than this molecule. So these, our first example are all ones we've already shown in the previous lectures, and then we'll do a new set of examples. So here I have molecules that we've looked at before. So our first one is the largest of all of them, and it has the most atoms. And even though it is in a ring circle, it has it has just more surface area than the other two. So this one has London dispersion forces, as does our London dispersion interactions. All of these, right? Because they all have electron clouds. The one that has the strongest London dispersion force interactions will be the one that is the largest. And so this one right here has the largest kind of intermolecular forces that are London dispersion. All right, next let's look at polarity and figure out which of these have a dipole moment that would have dipole-dipole interactions. So my first molecule has all carbon and hydrogen and carbon-carbon bonds, so it is nonpolar. My second one, we've seen already. It has 2 fluorine and 2 hydrogens, so we know this one is polar. And our third one is methanol. It has an overall dipole moment coming from a polar bond of carbon to oxygen and from hydrogen to oxygen. So this one is also polar. So looking at these, the only ones that have dipole-dipole interactions are the molecules that have are overall polar. So it's hard to say which of these is the strongest, although I would say most likely when comparing these, the carbon and fluorine will have a pretty significant difference in electronegativity. And so I would say it would have the stronger dipole-dipole interactions just because the electronegativity differences are greater than carbon and oxygen. But we won't need to compare the strength of the dipole-dipole moments in this class too much. We're just kind of doing this for completeness. All right, last up, we're going to look for hydrogen bonding interactions. Hydrogen bonding interactions, remember, only happen when there's a nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond within the molecule. And so our first one has only carbon-carbon and carbon-hydrogen, so none there. Our second one has carbon-hydrogen bonds, but not fluorine-hydrogen, nitrogen-hydrogen, or oxygen-hydrogen, so none there. And our last one has them in between an oxygen and a hydrogen. And so this will have hydrogen interactions. Okay, so comparing these three, I would say, because these are additive, our London dispersion are the weakest and our hydrogen bonding interactions are the strongest. I would say that our strongest intermolecular forces come from the methanol. And our weakest ones come from the one that has just London dispersion forces. Granted, it's the biggest molecule, but it only has one type and it's the weakest. So I would say our weakest interactions are from our benzene, the one that's just carbon-carbon and carbon-hydrogen. And so we'll use this information then later to say, oh, well, I bet that the one with the strongest intermolecular forces has the strongest boiling point. Let's do a second example, one that we haven't seen before. So I have two molecules that we'll be comparing this time. So let's go through and decide for each of our types of intermolecular forces if they exist and just list them underneath, and then we can compare. So both of these have a lot of atoms, and that means that they are going to have London dispersion interactions for both of them. All right, let's look at the overall polarity of the molecules. They're written in 3 dimensions already, which is great. I'm going to go through and identify my polar bonds. And I would do this by taking the difference in their electronegativities. I know that all carbon-carbon bonds are going to be nonpolar. And we previously looked at the difference between carbon and hydrogen, that it is also nonpolar. It has a difference of 0.4. Our carbon-oxygen will be polar because that'll be 3.5 minus 2.5. That equals 1.0 for our electronegativity difference in that range of 0.5 to 1.9. And we also have an oxygen-hydrogen bond, which is going to be polar. 3.5 minus 2.1 for a 1.4 electronegativity difference. So I can go through and determine which of these have polar and nonpolar bonds. In our second molecule, we also have a carbon-chlorine bond, which will be polar. Our chlorine is 3.0 and carbon is 2.5. So that's a difference of 0.5. So it is polar. It's kind of on the lower end. All right, so I'll go through and I'll identify my polar bonds. I've got one here between carbon and oxygen and between oxygen and hydrogen. And we've got another one right here. Now my other molecule, we just have one between the carbon and the chlorine. And so for both of these, if I'm looking at them, they both are going to be overall polar because they have just one or 3 polar bonds and then a lot of non-polar bonds to kind of balance them out. So they'll both be overall polar, and so therefore they'll have dipole-dipole interactions. Say the stronger dipole-dipole interactions are with our first molecule because there's a greater electronegativity difference in those bonds than we saw between the carbon and the chlorine. Similarly, it's a larger molecule, so it's likely to have the larger London dispersion forces. Although a chlorine atom is larger than an oxygen atom, there's still quite a bit more on the first one. All right, lastly, we're looking for hydrogen interactions. And so we're looking for something that has a hydrogen bonded to nitrogen, oxygen, or fluorine. And in this one, we've got one right here, and it's our only one. Those carbon-hydrogen bonds won't count. And in our other molecule, we only have carbon and hydrogen bonds. So we only have hydrogen bonding interactions or hydrogen interactions for our first one. Now we can compare these two and we can say, well, one has just more types and they're stronger. It also is just stronger on the ones that are the same. So we're going to have stronger intermolecular forces for our first molecule.